theory. And these blocks I call chemistry models for sustainable concrete technology. And so actually focuses on engineering, what I told you, concrete technology, but for that we actually need a lot of chemistry and chemistry models. So it will be quite actually also deep in chemistry, but everything very practical for to apply it as an engineers in concrete technology. So this, we are here, first day. And I always like this to present this slide because actually what we are doing is material science, chemistry of materials, and then also for the construction, cementitious materials mostly. And especially we are doing multi-scale reactive transport modeling. This is my specialization. I was always a big fan of these models because we actually need them a lot already from hydration. So here we have the atomistic. This is also what we do, atomistic modeling. And then we have this characterization, microstructure, very important for because what I told you, it's a material science approach. That means that we go from the structure to the properties. So from the structure, we want to predict the property, the engineering property for the performance of concrete at the end. And that we have, of course, the heart of the concrete. This is the cement paste, which is reacting. We have to characterize it, all these pores, nanopores, gel pores, capillary pores, solid volumes. We have this Heimerstruck model here, famous, which we developed with Professor Kunders in TU Delft, and which is actually already outdated, but yeah, that's why we have now new models I will show you. And yeah, also mesoscale, when the aggregates come into the picture, this, and then all this defines the property, or that, for example, the structural service life, where, for example, the steel corrosion is important. And we again have the diffusion of ions through the porous media, and this is exactly the reactive transport modeling. So the learning objective, so this was all just introduction. Now my teaching objective and your learning objective is that, and I'm also learning, of course, with you, and it's about the sustainability challenges, to address the sustainability challenges in cementitious materials. So this is the main, I'm sure you will have, your future jobs will be in this, because this is simply everywhere now in the industry. It's about the sustainability and how to go to net zero, how to abet, or how to avoid these CO2 emissions, or actually how to use CO2 as a friend. That's the most, this is what I see mostly. I will show it later in the slide. So really to use this carbon capture utilization techniques, technology, and for that you really need to understand and apply. So this is what I would like you to learn, not only to understand, which is the theory, a little bit better understanding, but I want you to apply it. This is why I also have these Python codes, and we have these tutorial sessions. This is one level higher in learning. So first you have to understand the theory, and then you can apply it. But actually it goes together, because when you apply it, then you can also much easier to understand the theory. So this is an easier way actually to learn it when you already start to applying it. And we talk about applying the chemical principles, computational methods, and measurement methods. So this is the instrumental methods. So this is the characterization part that all blend in. And at the end, you all need this kind of knowledge to analyze chemical properties of the materials, and this is important for the raw material selection. So which raw materials you will use for cementitious materials. We have these supplementary cementitious materials, for example. We can also use industry, secondary industry wastes, or byproducts. If they are used, then they are not wastes, they are byproducts. And you can, for example, carbonatize them, so you can completely avoid clinkers, and you can use slags, for example, with carbonation, and those are carbonatable binders. So you don't even have clinker, you just use raw material, and you can utilize the CO2 to produce materials. This example I will show you later, but so it's the raw materials, the production, and also use. So this is the use phase. For example, the durability is important, and reuse. So where we can have the recycling, and that's where the sustainability, of course, is also very important for recycling. So this is the learning objective. Any questions or comments? So this is the challenge, let's say. Then I will dive in to the first lecture block. This is the concrete technology motivation. And then later I will really dive into the chemistry models. Those are the calculation fundamentals that later after lunch break you can use it. I will then explain the Python and then show you the codes in Python I prepared for you, and also some online tools, online softwares like Frixie, but online, very easy to use, or games, but we don't use games. We will use, there is Tsem Games app, and this is a very useful. I hope you already registered, that you can, very hands-on, very easy to use app that you can apply the full power of the thermodynamic modeling. So it's about the phase assemblage prediction of the cementitious materials. You can predict all the phases which you develop for different the mix designs, reactive from the cement paste. So yeah, cement and concrete technology, how they plant. Of course, the cement, I don't have so much time to talk about clinker production, which is more chemical engineering, but yeah, we just start with the composition of clinker. Of course, in cement we have also gypsum. You will learn why. Probably, maybe you even know why. Just to regulate the setting. We have the fillers and supplementary cementitious materials. Those are our putzolans that help us in sustainability or industrial byproducts. And actually in cement technology, this is the biggest, where we have the biggest CO2 emission. And of course, the industry, especially here, very nearby us, is the Heidelberg cements, Heidelberg materials. And they are really, I would say, the most further as an industry in utilizing, making new industrial processes to utilize CO2. They really apply it in the, they're upscaling it to the industrial scale. So how to really utilize how to capture the CO2, but in my opinion, capturing is not really, it's already outdated. We need to integrate already technologies that can directly utilize the CO2. So not just to store it, but really to make benefit of the CO2. Example of what I showed you, what I already told you, but I will show you later, is the carbonatable binders, for example, where we can also have a CO2 as a binding reactive component to make binders that harden under carbonation. Yeah, there is also recycled aggregates or other, like how to make from the recycling fines, how to make reactive putzolans, then you can also utilize CO2. Rheology, this is a very important concrete technology principle. So it's a fresh concrete technology. You need to, of course, the success of concrete is because it hardens, it has a setting time, you can make it workable, and then after some period you can cast it. It's flowable, you cast into the mold, and then to cast it you need flowing properties. This is the fresh rheology, and later it hardens. So it's actually amazing material, man-made material. That's how we can make rock-like construction materials. And but the chemistry and the science behind is very amazing, actually. And Yeah, here you have a lot of also additive, of course, plasticizers. I will not go that much deep into it. I will actually just a few slides later, I will show just, you know, crash in course for the rheology because I find it, but I will more focus on the cement paste. Actually, I will also say a little bit about concrete and aggregates, how they affect rheology. So these are metal cellulose. Those are the stabilizers that we want to avoid bleeding because plasticizers, they, if you make concrete too much flowable, of course, then you have segregation because we have aggregates and water much high difference in densities and cement. So we need to have a stabilizer. Otherwise, they would segregate, meaning that the water would be on top and you would get concrete on or aggregates on bottom. Of course, there is also spraying concrete, very important to have good pumpability and also that it sticks to the wall and also it hardens fast. Yeah, this is the bleeding concept, what I told you. If you have segregation, then on top you will have the also the water on top and also the aggregates will fall down. But I will also tell you about this chemical shrinkage, very important. So from the total volume, actually there is a small chemical shrinkage, which actually also is inside. But there is a bleeding and chemical shrinkage actually makes you this water also from the, when you do the curing, very important to do the curing of the concrete because then you have additional water that comes into the concrete that allows you further reaction. I will talk about it later. I just want to here stress the most important concrete technology parts. Then we have the cement hydration. Yeah, of course, we need to adjust or tune the hardening by, we have the accelerators and also setting time accelerators, and we also have retarders because in warm periods we don't want this concrete to harden in this mixer. So we really need to control not only the rheology but also the setting of concrete. Then there is durability, and yeah, also important for the sustainability, but durability is also determined by the microstructure. So all these parameters before determine the durability, also rheology, because we don't want to have, we want to have a very dense concrete material that doesn't allow penetration of aggressive agents or chemicals, and we don't want cracks also. And in the end, yeah, here maybe just to say we have the also entrained air, which actually help durability because those are very small air bubbles that are very nicely distributed, and actually they also help rheology but also help durability because those are the closed pores and very nicely distributed, especially for freeze thawing, for example. If you have freezing like in Germany, now it's around 0 temperature. Yeah, of course you need some very finely distributed small volume where you can the ice can you know, grow the crystals. And this is called entrained air, which is different than entrapped air, which is actually non-uniform and big, and this is I would almost call it segregation part, where we don't have good rheology, and then we are actually entrapping air, and this is yeah, it's due to insufficient compaction. So those are not good, but the entrained air, which are introduced by chemicals, those are good for durability. So this is a very big overview of cement concrete technology. And now we will dive into the, before we go to the theory lectures, I want to show you one cement concrete decarbonization roadmap. This is, I was inspired by Heidelberg Cement. They made something similar, but I even more adjusted it and bring it further. So this is my view on cement concrete decarbonization. And gray would be the business as usual. So we have the cement industry, of course, very high CO2 output because we are burning limestone. We have industrial byproducts that we use as SCMs. This is already old. That's not, it doesn't help us anymore to really reduce CO2. This is already like state of the art. It reduces the cement clinker, of course, but this is we need to go beyond that. So, for example, calcine clays, yes, sure, nice, but we need new technologies. And for this, I mentioned you, for example, these carbonatable binders. So we have the concrete industry. This is the gray zone, which is business as usual. But of course, we need also the green part. They have to adapt to new raw materials, new cements, and also the durability and how we account for durability and recycling. This is the new part because mostly concrete was okay. It's now being a little bit used with for recycling of aggregates. This is that's why this part is the gray part. But actually the new part, which is much more interesting, would be really to use concrete, recycled concrete as a carbon capture and utilization. And here, so carbonization, mineralization, here we could actually reduce to 5% of the CO2 could be stored from this 8%. So we could almost make going to net zero concrete. And here I mean like, you know, to use CO2 for concrete curing, for example. This is already technology that's being in upscaling. I also saw in US, in California, they are pushing this technology as a new technology so that you can, you know, cure concrete even during mixing and then store CO2 and improve the properties of concrete. Another way is, of course, to not to directly use recycled aggregates, but actually to carbonatize them, store CO2, and then use them in concrete. And even more is you know, from the recycled concrete, you have a lot of, almost 50% of the fines, which you cannot use in the sand and aggregates. And those fines can be actually carbonatized and then used as a new SCMs, because we have a lot of, you know, CSH. And if you introduce CO2 reactors in carbon capture and utilization, those CO2 actually converts the SCH to, so the main mineral from cement hydration, the calcium silica gel, it converts it to silica gel and calcium carbonate. And this silica gel actually is a very reactive putzolan. Then you can use as the SCMs, and then we again have a closed loop. So this would be the green improvements for the decarbonization of cement and concrete industry. And here I would mention some new materials, of course, fly ash and all this silica fume. This is old story, slags. But here we have the steel slags, which are actually not reactive, but if we, this is very interesting because those you can also carbonatize and then you get reactive. You can even directly have a carbonatable binders by using steel slags. It has a lot of gamma C2S, which is actually not hydraulically reactive, but under CO2 or acid conditions, they actually are reactive, very reactive indeed, and they form then also silica gel and calcium carbonate and some CSH gels, and this then is the new carbonatable binder that can also harden by using no cement at all. Do you have any comments or ideas on this? I would also like to hear your side.
You're audible, sir?
Yes.
Yeah. Yes, sir. Participants, any questions anybody wants to ask? On these slides,
Okay.
any query?
How many
Sir,
of...
participant has one question, sir. I'll just...
Yes, perfect. Thank you.
Professor, I needed to know about the how uh, we can know about the different types of industrial byproducts, whether uh, are they quant, are they available in good quant to utilize in concrete?
Yes, thank you for this question. It's always about the quantity, of course, because we have a huge, we need a huge quantities, and the cement industry is not interested if there is not a huge amount of it. So yeah, steel slags, we have quite a lot of it. I now don't know exactly the number in my head, but it's also a growing amounts of it. So yes, but you are right. The quantity is very important. I agree. We also have our switching from different types of steel slags, BOFS, for example, and yeah, there are different type of burning technologies or the melting technologies, and there is also a trend to transition to another way of technology. I hope this answers you. Okay, then I will continue. We have a lot of cement chemistry.
Online participants can type their questions in the chat box.
Yes,
Online
that would be great.
participants, they can type their questions in the chat box. Yeah. So you can
Yes,
continue,
please.
sir. Yes. Yeah.
Yeah, thank you. Yeah, please type the questions. So now we deep dive into the cement chemistry, cement hydration. I hope even if you don't have any background, now you will be able to model at the end of the day the cement hydration, even just by using CEM games at the end, but just that you know you have some backgrounds, what's going behind, even when you use already hands-on apps, that you know what they are calculating. They are calculating everything for you. You can really with few clicks you can get very good modular results, which you actually can easily use to publish papers. It's really that simple. Games is a bit complicated to use, but really with this app, you can, what I will show you at the end of the tutorial, this app, I hope you already registered, you had some trials. You can really, what I told you, yeah, with few clicks you can model your systems and publish these results in, the papers I saw in thermodynamic modeling are mostly not different than what you could do actually with this CEM app. But yeah, of course, you need to know the background, how they are working to really get the most of it. And especially if you want to really model something new. And yeah, then you also need to know how to model. And you cannot only, these apps are very useful, very easy to use, but they are also not so flexible. Because if you want to change, for example, model the carbonatable binders, of course, they are not yet implemented in this kind of apps. So then you really need to develop your own model and understand all the theory behind that you can make your own carbonation model, for example. Then this is why I now go through the theory so deep. And here we can see this is from Switzerland, from Robert Flat group. Very nice sketch. And we have here the model, the cement. clinker, which is basically, you will learn today, is the 3-calcium silicate and 3-calcium aluminate. In the most simplest form, of course, we have also iron and other minerals, but let's say just the most simplest, we have the calcium silicate and calcium aluminate. So let's say 2 parallel reactions. One is the, we call it in a simplified way, silicate and aluminate reaction. And yeah, we need gypsum or hemihydrate because we want to regulate the setting time. And we have the water, and when you mix this, we have these amazing reactions that actually, first we have the dissolution of the minerals. So we have the ions, the calcium, silicates, ions, they are here. Aluminate ions, they are all dissolving from the minerals. So it's dissolution of minerals. And we have them in the pore solution, it's called. So in the solution, or pore, because it's inside the pores. And then when they become saturated, meaning that, or actually we need to oversaturate because we have these nucleation barriers to form the first nucleus. And when we form the first nucleuses, then we start to precipitate. It's called precipitation of the hydration products, like for example portlandite crystals. We have the calcium silicate hydrate gel. This is the main, it's called CSH, or cash if you have aluminate phases, a lot of alumina inside. And we have the ettringite. So this is the aluminate hydration product. So basically it's a dissolution, nucleation, and then crystal growth. Or we have here amorphous precipitation of amorphous gels that then actually increase the solid volume, and that's why we have the hardening process of the cementitious materials, of the cement paste. Let me go here. Yeah, here of course we need to add chemicals, and these are the plasticizers if we want to control the rheology, or also the setting time. Actually, they also increase the setting time, so we need to add more additives to then, because this 20-hour working time or 15-hour is too much. We need to, after a few hours, the concrete should start setting and then also hardening. And we can control the hardening, the rate of hardening. So there is the setting when it's you know, the setting is when the time when you cannot, it's the end of the workability, let's say. And then you have the hardening, and you can also, you can have a, you know, very long setting time but very steep hardening time, or very low hardening setting time but very slow hardening. So those are all things that you can control with different additives. And then the question is, yeah, how to predict the setting time. And also, I will not go to that deep in this chemistry of organic chemistry. You can just imagine these plasticizers as a, you know, as a chain, and we have also these back chains, and those plasticizers are negatively charged, so they can absorb on the cement surface. So just now a little bit about the rheology. You know, Newtonian liquid, if we have here shear stress and here shear rate, the Newtonian liquid, like water, we don't have any yield stress. It just starts to flow as immediately as we have some shear rate. But typically the cementitious materials and also concrete has Bingham or type, so they have a plastic, they have this yield stress, so you need a certain amount of shear stress to initiate, and then it starts to flow. Typical example is also, for example, ketchup. You want to get out the ketchup out of the bottle, so you really need to make some you know, vibration or some stress so that it starts to flow. So this is exactly the same thing for cement paste and concrete. And we actually also measure this by the slump flow. And here I would say if we have, this would be just typical behavior, but we also have, I will draw this, try to draw it, maybe with a bit thicker. So this is if we have shear thinning. So shear, that's the thixotropy, and cement paste is the shear thinning, and also what I mentioned before, ketchup. So the more energy you put into it, the less, the lower the viscosity. So actually the shear thinning would go like this, in this direction. So the more shear rate, the lower the viscosity. The viscosity, plastic viscosity, is actually the rate, the slope of this curve. So we have a constant plastic viscosity, and here the plastic viscosity is actually decreasing. But the concrete, actually, because of the aggregates, because we have this aggregate effects and all the, the capillary forces, actually this is shear thickening. So the concrete goes like this. It's a shear thickening because of the jamming of the aggregates, and also the, the, how it's called, the dilatants, yes, that you have the volume increase and the formation of capillary forces. You have actually at the end shear thickening behavior. That means that when you actually even want it to flow, that you put more energy, but then it actually stops to flow. But this is the example of the normal concrete. But of course, in the self-compacting or other flowable concretes, you don't have this shear thickening so much. Or you can have, at the beginning shear thinning and then later shear thickening, different combinations. So that depends on the concrete type. So this is what I was saying, that you have this, the slope of this curve is actually the plastic viscosity, and you can see here that if you put plasticizer, this in German Fließmittel is plasticizers, you are actually increasing or decreasing the plastic viscosity. But of course, you are also decreasing the yield stress. So, and here we have different concretes. So if this is the range of conventional concrete, this would be the segregation zone where you don't want to be. For example, you have too high viscosity, and then you are actually segregating. So that's why you want to put some, the viscosity modifiers like cellulose, that you are increasing the yield stress, but also you are increasing the viscosity, so that you don't have the segregation zone. But if you want to make a self-compacting concrete, actually you want to have actually very high plastic viscosity but very low yield stress. And you need this high plastic viscosity because you don't want the material to segregate, and this is where you actually really need to apply your methyl cellulose, so the viscosity modifying agents. So now the reason why we have such a behavior is basically the flocculation or the aggregation of the particles at cement paste. So we have this, that the cement particles, they are not fully dispersed. At the beginning maybe yes, but they actually make flocculates or aggregates. They start to aggregate, and we are building these kind of networks. And this is why we have the yield stress, and this is why we also have changing the thixotropy. That explains also the thixotropy, because if you put some energy, you will break this kind of bonds. And especially there is also hydration part. So that's the yellow part, which actually makes stronger the bonds, the CSH nucleation parts at early hydration. So you are creating the networks which are stronger, but when you are sharing, increasing the share rates, then you are breaking these kind of networks, and that explains basically the thixotropy behavior. So here we can see this kind of nucleation. CSH is the yellow part, And those are very, very small particles which nucleate, and they preferentially nucleate exactly at the contact points. That's why very, very little of CSH for a long time. I think still scientists today doubt that there is any CSH on the surface because it's such a small layer that you cannot even measure with the most modern techniques. But of course there is really this kind of contact points which are below nanometer, and they are really important for the rheology. So this you can see already 2008 there is this focused ion beam scanning electron microscope where we can have you know, with just scanning electron microscope here. I think this is backscatter, so we can see that the white is the more lighter elements, the cement particles, and the black are the pores. Or actually maybe it's the CT, but it doesn't matter. Maybe it's just secondary electrons. I guess it's secondary electrons then. But yeah, just remember the black is the pores and or the water, and this brighter is are the cement particles, which we can see they are very irregular, and in this case they are fully dispersed because we use the plasticizer here. But here we don't use plasticizers, and you can see that the cement particles are flocculated. And with focused ion beam, basically it's a one beam that removes layer by layer, atomistic nanoscale layer, and then you can image scanning electron microscope after removing layer by layer. This was the new technique in 2008. I think nowadays it's becoming more and more common. So you get this kind of 3D, it's called nanotomography. This is the really nano, because you really get, it's not the micro CT, it's really you are using the scanning electron microscope, and then removing with focus ion beam, you are removing layer by layer, and then you can get really this kind of 3D images at the nanoscale. So this is also for the characterization of the materials part. That's why I'm explaining also these characterization techniques. And here we have the plasticizer inside, and why do they work? Because this, especially this second generation, they are called polycarboxylate, because we have this adsorption of the polymer on the cement surface, but not only of the main backbone chain. We also have these steric effects, because then we have even more better dispersion of the cement particles. So this was a big innovation, like, I don't know, 100 years ago almost. Before we only had the adsorption of, let's say, monolayer adsorption, but nowadays this kind of side chains allow us also to better control the rheology. So the cement, yeah, this not only single particles, they are actually polymineral grains. So even one particle has a different mineralogy. So there we have the C3A and C3A. They can also be in one particle. So there are multigrains, and we also have the angular, so they are irregular, and we also have many minerals in one single particle. So after clinkering, we need to grind it. Of course, the grinding is also very important. How fine the cement particles are, the finer, the more reactive they are. And then after grinding the clinker, we also add during the grinding the gypsum is added, because we need to regulate the setting time, and also the supplementary cementitious materials are grinded together. And about the SCMs I will talk about tomorrow. I have some background noise. I don't know if... Yeah, very nice. Thank you. Now it's much better. So C3S, this is the main mineral. And if you want, this is just a cement shorthand notation. Now the noises are again starting. And in this shorthand notation, actually C means calcium oxide and S is silicium dioxide. So in shorthand, it's just we have 3 calcium oxide and 1 silicium dioxide. But the correct, actually, if you ask chemists like Johann Planck from TU München, he's very famous, I think, in Germany for as a chemist, and he actually suggested this kind of formula, and this is because you have actually in the crystal. So it's a 3-calcium oxysilicate, because in the crystal, when you want to see what is really building this kind of crystal, you will have actually the building units are the tetraeder, silica tetraeder. That's why you can see here directly in the formula the building unit. You have the calcium, and you have also the free oxygen inside. And this actually free oxygen makes the C3S very reactive. So if you want a real chemist notation, this would be the best way to represent it. But in the cement chemistry, of course, we are engineers. We just want to make it simpler, and it makes also very much sense to have this simple notation, because it's much easier to remember the chemical reaction later than if you are using this kind of chemist notation. Then everything becomes looks complicated and much more difficult, but here it's much easier to write chemical equations, what we will write later. So this is the halite, actually, is the impure modification of C3S. So this halite is not a pure mineral. It has impurities, and actually they also are important to stabilize during the crinkling process, to stabilize the formation of halite. Otherwise, we would get the other crinkle minerals during the burning process. And we also, foreign ions are also important for the reactivity and also for the stabilization, so that we can create more of the C3S at lower temperatures. And yeah, we have also different minerals like C2S and also C3A. And if you would plot the compressive strength development with time, you would see that actually C3S is the main, the most important mineral that reacts and that gives the highest early strength. Other minerals are also important. For example, C2S gives the later important for later strength, but also from sustainability point of view, it's also interesting because it's burned at lower temperature and demands less CO2, because we have less calcium carbonate to burn. And we have other minerals because they are also present. Do you know why they are present? Why do we have these aluminates? Can you tell me? Of course, if we can make a pure cement, would be much better. And this is actually what we have in enlightenment, C-lightenment. This is our student Zimmerman. He got PhD, and then now he's working in this C-lightenment, which is actually pure calcium silicate. And then we don't have aluminates, which is also good from the durability point of view, because you don't have the delayed ettringite formation. Because ettringite you need, so it's from the durability point of view, would be much better to have only silicates. But why are they aluminates? You know why? Because we have raw materials for the production of clinker is not only calcium oxide and silicates. We are using clays, and in clays we don't have such pure clays. There are always impurities and especially aluminates in the clays, and that's why the technology to produce cement is always based also on aluminates. It would be very difficult to have clays or silicates, only raw materials, or very expensive. This is why we always have aluminates, and they are actually, if you don't use gypsum, you would have a flash setting time, so they would react immediately. and then you would directly, you know, that mixer, it will be directly, you would even not be able to fill the mixer. The truck, it will just, the second you add water, it would form calcium aluminates, hydrates, which are without sulfates, they directly set. So it's called flash setting. So that's why we need gypsum or sulfates, that we can control this reaction, slow down this reaction, and then, but they also contribute to a little bit to the strength. So this is also then good. So now let's write our first reaction. It's a through solution, but if we want to keep it simple, we want to know which kind of, when we dissolve these ions in water, we want to know which kind of products we have. And you can calculate these thermodynamics from the reaction thermodynamics, from the theory. Actually, that will tell you what kind of products you would get if you have these ions in a solution. And this is why reaction thermodynamics is important, and this is what it can tell you. It can only tell you what is the equilibrium, in equilibrium, what kind of products you would get. Of course, if you have an open system, that means that there is also CO2 involved. The through equilibrium product would be, again, calcium carbonate and silica gel probably. So this would be equilibrium. So that's you go back to the original raw materials, which when you burn, you increase the energy, and that's why they react, and then they precipitate portlandite and silica gels. But if you would have CO2, the equilibrium actually would be calcium carbonate. So you would even not form, if you ask thermodynamics, what is the product, equilibrium product, when you have calcium and silicates in the solution, and CO2, an open system, that means that the CO2 can go inside, you would get calcium carbonate as a final product, and silica gel. Or even a quartz, it depends what you know. But this is because of the kinetic reasons, because the carbonation is so slow. So this is where the kinetics jumps in. So those are the most important in chemistry. First is what is the equilibrium, what can form, what is available to form, or we say what is spontaneous, what is to form. That is the answer of thermodynamics. So then you will know what kind of products you can get, but what you really get. So this could maybe take ages or forever to get, but what you really get, this is because of the kinetics. So the thermodynamics only tells you what you get in equilibrium, finite equilibrium, but you can trick it, because if you remove the phases which you get at the end, for example, if you would remove calcium carbonate or CO2 simply that reacts, then you would get metastable products. And actually the cement hydration is a metastable, because that's why we have the durability problems, because the final reaction is the calcium carbonate, or it forms some other expensive products that then destroy the concrete. And then the reaction, the kinetics, is actually the most important part that defines what kind of products you really have, even in terms of hundreds of years. The kinetics is still defining that you still have, you know, cement reacting, and you still have portlandite and CSH as a metastable phases actually. So this is our first reaction. We can write, and it looks very simple when you write it in a short cement chemist notation. And here, this is the portlandite CH, very simple. And we know this is the CSH, calcium silica hydrate. And this is a crystal, well-known crystal, which has a well-defined stoichiometry. But here, actually, this calcium silica gel is amorphous, and it also has variable calcium silica ratios. So depending on the hydration time, temperature, or the time when you react, you will form also different kind of calcium silica ratios. So this is always, let's say, variable composition of calcium silica hydrates. Mostly it's taken to be 1.7, 1.8. It depends also if you have puzzolans, of course, this would be lower. Depends on the amount of calcium to silica you have in your clinker. So now you can write, I think this equation is easy to write. If you know that you have to define, the calcium silica ratio, and when you define the calcium silica ratio, then you can also balance the reaction, and then you know that you need to have 1.2 Portlandite here, because when you sum 1.2 and 1.8, you have to get 3 here. So here you have 3 calciums, and then on the right hand side you also should have 3 calciums. And when you define here 1.8, that means here this stoichiometric coefficient actually is 3, which is here, minus 1.8, so it's 1.2. So this is how you balance the chemical reactions. But if you have more complicated, I will later in the tutorial, I will show you how you can calculate by solving system of equations, how you can balance chemical equations. But now you got the gist of it, you basically just have to balance how many calciums you have here and how many calciums you have on the right hand side. And now, because in chemistry, we are working with molar masses. You know why? Because the atoms are reacting. The mass it's not defined by mass. The reaction products and all the reactions are defined by atoms. So you need to know how many atoms of calcium reacts with how many atoms of silica. And this is defined by molar mass. The molar mass tells you how many moles, which basically means how many particles, how many atoms, how many moles you have in 1 gram. For example, the molar mass of hydrogen is 1. This is the reference. And this defines you that in 1 gram of hydrogen, you have the Avogadro number of atoms, which is, this number. Now I forgot it exactly, but it's some number to the power of 23. So you have 10 on power of 23 zeros, 1, and then 23 zeros of atoms in 1 gram of hydrogen. So this is the reference. This is called the Avogadro number. And then instead of just, using 10 of power 23, that's why we have the mole definition. And we have the molar mass. So that's why we are working with moles, because the atoms are reacting. We need to know exactly that we should have 1.8 times more atoms of calcium than silica. So we cannot just say the masses. We need to calculate what is the ratio of the masses that we need to mix to produce this kind of ratio of calcium silicates. And this is why we need to work with molar masses. And if you want to now calculate the stoichiometric amount of water that reacts with halide or C3S, and stoichiometric means that it fully consumes the C3S, so the full reaction, that it would stoichiometrically react, that it means that the number of atoms of C3S and the number of atoms of H are the same, that would then form this kind of hydration products. This is the stoichiometric amount of water that we need to mix to fully react the C3S. And this is very engineering interesting property. And you can now calculate it just by the ratio of the molar mass divided by the mass of C3S. This is what you would do if you are not a chemist. You would just want to know the mass of water divided by mass of C3S. But actually it's not the mass, it's the molar mass and multiplied by the stoichiometric coefficients. So that's the whole idea about the chemistry. You just need to know that you have to work with molar masses, not the masses, and then also with the stoichiometric coefficients, because here we have 5.2. That means that we need to multiply this molar mass with 5.2, because we have 5.2 times more atoms here. So this is why we need to multiply these atoms here with 5.2 and then relate it to the molar mass and the number of, which is 1 here, stoichiometric coefficient is 1. And then you would get the, what is the stoichiometric water cement ratio that you need, how much water you need to fully react C3S. Those are just the molar masses. This is the stoichiometric coefficients, and you need, this is the water cement ratio of 0.41. This is also well known from the Powers model. So this is the amount of water you would need to fully react the cement. If you have less water than 0.41, the cement cannot react. And then we say that the limiting reactant is water, because you will have the unreacted cement at the end. If you have too much, if you have stoichiometric or more water, then you have actually the limiting reactant is then the cement, because then you have extra water. You have unreacted water, which gives you the capillary pores and poor strength at the end, because you have too much water in the system. So now we can use the same principle. I will show it further in tutorial. For example, you want to know, okay, how much CSH if I'm reacting 1 gram of cement with 0.41 grams of water, how much CSH do I have in my mixture? So now you can use the same chemical principle. You just need the molar masses. So it's the molar mass of CSH divided by multiplied by the stoichiometric coefficient divided by molar mass of cement, because you want to know how much CSH per gram of cement, and you should not forget the stoichiometric coefficients. Basically here are 1, so basically you are, if you divide molar mass of CSH, which is 228, no, sorry, this is C3S. Molar mass of CSH, I don't know now, if you divide it by the molar mass of C3S, you would get the amount of how much CSH you get per gram of C3S. So it's gram per gram of C3S. Gram per gram of cement. If you want to go for paste, because we want to know the molar, what are the masses, or even we want to know the volumes, we just of course need the density. That's easy for you engineers now. But you now, to go from the gram per gram cement to per gram of paste, you just need to divide by the 1 plus water cement ratio, because you are increasing your system with water. So that means that all your masses, you have to divide by the 1 plus water cement ratio. How much you increase your system. So if the system now is paste, not only C3S, you just divide by the 1.4 T1. Then you will get the mass of CSH in your cement paste, which is exactly what you want to know. How much, I don't know, you want to know how much chemical shrinkage, how much porosity you have in your cement paste. So this is how you can calculate it. Any questions here? So this is very the core of today's lecture, that you really understand how to calculate using simple, very basic chemist principle, and then you can calculate the phase assemblage of cement paste. And this is now in stoichiometric condition. That means that we have a full reaction. I think it's you just need to remember this slide, or you have a look later, and then you can just implement any kind of calculation. Let's say like this. Even if you don't get it now, just follow this slide and you can calculate it very easily. But this is without the degree of reaction. But if you have the degree of reaction, you just need to multiply with the degree of reaction. Of course, the left-hand side, if only 50% of the C3S reacted, you just multiply your result here with 50%, and you will get how much you have your unreacted C3S, or how much of you have your unreacted water. On the right-hand side, of course, we need to use 1 minus degree of reaction. because here we have our unreacted parts.
Sir, one online participant has raised a question in the chat box.
Yes. Let me read it. If I decrease or increase the percentage of gypsum in the cement chemistry, then what will be the change in the inside chemistry of the cementitious matrix? This we will actually have an example later. We will calculate this. But let me just answer now roughly. So we need optimum gypsum also to to have the optimal strength and also the setting behavior. And I will actually show this in few slides from now. So I will just please wait for a few slides, because I have you can also determine this optimum gypsum by the calorimetry. I will show it on the slides better than now explaining.
Professor,
Yes.
one more question.
Yes, please.
Professor, nowadays the industries are producing different kinds of cement, like they are adding SCMs or various kind of byproducts. Will they give us the exact water cement ratio value?
No, but you can calculate. And this is the topic for tomorrow, because tomorrow we will talk about the SCMs the whole day. First, we will talk about the kinetics, and then I will talk about the putzolanic reactions. And then actually you can see, yes, you would then be able to calculate.
Thank you.
So please, yeah, be patient. We go step by step, because this is very important for me that you understand this, that you can always remember, go back to this slide, and then you basically can do chemical calculations. I know it's very fundamental, but this is very important that for later that you capture this. So yeah, this is what you can then calculate. We will calculate this using the Python in Colab. I developed the code for you. I will share the code for you. Everything, also the slides from me, I share everything with you. So yeah, later you can just use it. So even if you don't catch it now, the idea is that you have the slides and you can use it later. Also the codes. So I know this is a tough course, because actually what I'm summarizing is the whole semester course in only a few days. So it's I'm aware that I'm putting a lot of information to you, and that will be overwhelmed by it, I know, but I did it anyway, because I wanted that you have this information, that you can use it later. So this is what we can calculate, and you will calculate. I will show it, also demonstrate. So we can have a volume fraction of the paste. We see the volumes. Initially we have the cement mixed with water. This is the water cement ratio of 0.5, I think, because then from the densities you can get the volume fraction. Yeah, 0.5, you can see it here. And then as a function of the degree of reaction, we can calculate each of these points here, and we can get this nice graph when we can see how much CSH, how much Portlandite, how much water, and how much chemical shrinkage. Chemical shrinkage is very important, because you can see here it's almost 10% of the cement hydration by volume. 10% of the volume of the cement paste is chemical shrinkage. This is amazing, and it's always, people don't understand the importance of chemical shrinkage. But basically, it's an empty volume that you are creating, and that makes a vacuum. This actually sucks in that's why we need to spray concrete in applications, because this chemical shrinkage is then sucking in the water you are pouring on top. So 10% by volume of the cement paste is sucked in. So if you are not spraying concrete during the curing phase, you are basically have 10% of air inside, and then also the reaction is stopped because you don't have enough water, and you have capillary forces, you have the air inside, you have chemical shrinkage, you have autogenous shrinkage, so you have initial drying shrinkage. You have basic autogenous drying shrinkage. Basically, the concrete dries from inside, and you have cracks because of the capillaries. So this is the especially important for high performance concretes when you have low water cement ratios, because then this chemical shrinkage is very important. And the early shrinkage cracks, internal drying shrinkage cracks is, so it's called autogenous shrinkage, is very important for when you have low water cement ratios. And what is chemical shrinkage? Basically, it's the chemical fact that the sum of the water and cement at the beginning is bigger than the sum of the water of the reaction products at the end. So if you would sum what you have, the volume of water at the end and your hydration products is less than the volume of water and cement you put in. And this is why you have this chemical shrinkage. And this is it's empty pores. Basically, it's creating. It's because you know the cement paste or the concrete doesn't change volume. The concrete stays the same, so the system volume is the same, basically the same. You have a little bit maybe shrinkage, but this is you know promilles, very little. But the volume is the same, and if the volume is the same, you are basically creating empty porosity from the inside. So this is creating vacuum. It's basically creating volume out of nothing. It's actually, yeah, very amazing thing. But very important, very technologically very important. And if you would then sum the water, the remaining water, which is called the capillary porosity, and the chemical shrinkage, you would get the porosity. So it's not, the porosity is not only the water remaining, because I don't know, let's say we have the cement reacts only 80% after 28 days. So we have, you can calculate how much cement, yeah, you know how much cement didn't react, but you can calculate the amount of hydration products, you know their volumes, you know the amount of water, and you need chemical shrinkage. And then when you do the sum of chemical shrinkage and capillary water, you get actually the porosity. And this is called the capillary porosity. So this is what you can always calculate, and it's very important engineering property. But you should never forget that actually also the solid CSH has 25 to 35% of gel pores. So this is solid. If you would, in the, you know, when we talk about with the physical property, it's solid, but these pores are below the 10 nanometer pores. So it's almost like, you know, clay, gel pores. And this porosity is also very crucial for engineering properties of concrete. Because here you can explain also, you know, even creep or also shrinkage. So this is, don't forget that you have 25, this is the inner CSH, because I told you, there is different types of CSHs with calcium silica ratios, but also with time, you can have inner product and outer product, it's called. I will show you later in the growing shear model, growing shell, in the particle model, that you can have an inner shell and outer shell, and then the inner CSH is more dense, so this then has 25% of the gel pores, and the outer shell CSH is actually very porous because it grows in the pores. And even without the capillary porosity, if you only take the CSH part as a solid, you also have actually 35% of the porosity below 10 nanometers porosity. And now we can change the easily water cement ratio, and you will see that there is, you can calculate the stoichiometric amount of water. You can calculate the amount of unreacted cement because you consume all the water. So if you didn't spray your concrete outside, you you use low water cement ratio, and there is not enough water to hydrate all the cement. And don't forget, this model doesn't have any air bubbles. So the air bubbles, we have few percent, maybe in concrete, and I think up to 10% of air bubbles we can have in cement paste. So don't forget to add also air bubbles, of course, play a crucial role in the engineering concrete technology. So this is just the phase assemblage that doesn't include any air bubbles. So I don't know what time. Now we are almost at the end of this lecture. So maybe let me just check, maybe I'll go to answer your question about gypsum. So if you look at the colorimetry for the hydration reaction for gypsum, you can have, or let me explain it here. First, when you measure with calorimetry, for example, isothermal calorimetry, reaction calorimetry, you have the heat flow, this is the time, and you have this initial hydration peak, and then you have the second main peak, which is actually the silicate reaction. So initially very little silicate reacts. Of course it reacts, it also defines the rheology. What I told you, this CSH, very little but very important for the rheology because they bridge the particles. And then we have the main silica reaction. But the other is the aluminate reaction. And this is the green part. So actually it's mostly ettringite forms at the beginning. That's the gypsum formation. I mean the ettringite formation. We have the consumption of gypsum and then the ettringite is formed. But the sulfate actually also adsorb on the cement clinker and they block also aluminates. And that's why we don't have any more reaction of aluminates. But the moment you deplete the sulfate, so that's why it's very important to have the optimal dosage of sulfates. When you deplete the sulfate in the solution, or also the gypsum, which is dissolving, so when you deplete the sulfate, then you start again the aluminate reaction, because the sulfates then desorb from the cement surface, from the C3A surface, and then you have another reaction. So basically you don't have sulfates anymore which were blocking the surface of the C3A. That's why there is no flash set. But and then you have further ettringite formation, and then later you have monosulfate formation. And because ettringite is also a very big crystal that has a high amount of water, which has an expansion reaction, which is good for porosity, to block the porosity, which is good for strength. But if you have too much ettringite, then actually you have these expansion reactions that then detrimental for the strength. And this is why also you have this so-called delayed ettringite formation. When you have, sulfates attacking concrete, you have delayed ettringite formation, and then again, that's where you get these expensive minerals, which then crack the concrete. But you also need to have optimal amount here. If you would have too less sulfates, then you would have this reaction here. So this peak would be here or even before. And then this is too less. So by colorimetry, you can determine the optimal sulfate amount. It should be here. And if it's too much later, it's also not good. And you can see this here. So this is, then we are talking about undersulfated cement. If you have here peak before even the silicate reaction, this one is properly sulfated because you have mainly the main peak. But if it's oversulfated, then you have the C3A reaction is too late. You have it here inside. You should at least see it as a second peak here. If you don't see it, of course, you either have it here or maybe later. but you don't want to have over-sulfated system because then your strength goes down because of this ettringite expansion reaction. This is also very important for LCAs, LC3 systems. So when you have clay like metakaolin, because clay has metakaolin has aluminates, these aluminates react also very early, and then you have to adjust your sulfates in the LC3 system. Like you know the Scrivener mixture with the limestone, calcine clay, and cement. Then you can reduce 50% the cement clinker, but you need to again optimize the sulfate contact. And you need to know the reactivity of the clay, of course, very important. And this we will talk about then further, day 2. And yes, I think we are ready for the break, 50-minute break, and then I will continue with the slides and also go into the calculation. 1:15 is lunch break. What time is 1:50?
Yes.
Then I need to calculate what is the time here. 4.5 hour difference is difficult. Difficult to calculate. But okay, we have, how much do we have? Half an hour?
35 minutes, another 35 minutes, sir. 35 minutes.
35 minutes.
From
okay,
this
perfect.
time. 35 minutes, yes.
So till 8:45. Okay, perfect. 35 minutes. Let's then continue. So this is the literature I collected for you. Probably you know this microstructural analysis. This is very good tool for you can do all the characterization techniques if you follow this this book. Let me see if I missed something here. I think this is all. I will go directly then. Yeah, maybe here this we can do. So if you want to write the chemical reaction for ettringite formation, actually the only thing you need to know is how to write the gypsum. And if you know the C is calcium oxide, small s is sulfate. So that's why we have the C and then small s for sulfates. And we have 2 waters in gypsum. It's calcium sulfate dihydride, they call it also. So if you know how to write, it's in shorthand cement notation, then basically you know how to write the EFT. This is called aluminoferrite tetra. It's called tetra because we have three. We have 3 calcium sulfates. So basically it's C3A with 3 calcium sulfates and water. Yeah, water, you just need to remember that in gypsum, in ettringite, we have 32 molecules of water. And in monosulfate, we have 12 molecules of water. This is the only thing you should remember. And then it's very easy actually to write this equation if you use shorthand cement notation. If you use the real, then it's also would be difficult for me to write it. So just remember here C3A, which is just C3A. You have then the calcium, extra calcium in gypsum. And here we have now the monosulfate, which because it's the mono calcium sulfate. That's why it is called aluminoferrite mono. So this is the monosulfate. So which reactions do we have in cement? First we have ettringite formation, because we have gypsum. And when is the monosulfate forming? We saw it forming later. And this is when we have depleted what I told you. When there is no more gypsum, we have depleted it, fully consumed. Then this reaction takes place, is the monosulfate. This is if we would have carbonates. Actually, then now you can also write the monocarbonate reaction. Especially if we have limestone, you know, very fine milled limestone powder. which is almost every cement nowadays contains limestone inside. And then you can also, instead of just calcium sulfate, monosulfate, you can just put here a C, small c. The small c is from the CO2, from the carbonate. So then this is the, actually, this is the, then you have the monocarbonate. And then you can also easily write this reaction. We can write it later in the practicing tool session. So this is the only thing I wanted to tell you. This we already went through. Plasticizers, yeah, that's already explained. Maybe just, yeah. So this is the absorption of the gypsum, of the calcium sulfate on the C3A surface. So this is the sulfate here. The minus is the sulfate, and this absorption actually blocks the C3A reaction, and this is why we have the setting regulation time. But the moment the sulfate is depleted, this would deabsorb, and that's why we have strong continuation of the reaction, and that's why we have this third peak for the aluminate reaction, which is very useful in calorimetry, in that we can optimize the sulfate amounts, which is not very important for cement industry. It's also important for you, because when you use LC3 cement, new cements, then you have to optimize. Actually, the concrete technologies are doing this, because you are optimizing the concrete for LC3 mixture. It's not, so it's really, it comes to the civil engineers at the end that you need to know this chemistry stuff. Because when you do LC3, so the limestone, calcine clay mixture, you need to, I would suggest you do the calorimetry and check of the cement paste, and then check the peak, and then you can optimize the sulfate addition. Much easier than doing compressive strengths, for example. So here I have one, I wanted to do one, yeah, let's, maybe that could be a little break. If you can do enter here. Can you enter this? So if you go to Pingo and then enter this number, you just need 731074. We can do a small survey. Let me open this. Just to keep you, make you alive a bit. Let me find it. I'm here. Just wait, I need to make a survey. Let me start with okay, now you should be able to see the first question. If you can answer the question. So I'm asking you about the background. How much background do you have in Python? Is it working? Let me check. I can also check. So you should see this. Can you see this on the screen? So this is the question. How much background do you have? So you can answer this 0, some. Let me continue. Ah, okay. Now we are getting already some answers. Perfect. 0. Okay, so 70% have no background in Python. This is good. Beginner, very nice. Some. Okay, no advanced guys. Even I'm not advanced. I may be good in MATLAB, but not in Python. Yeah, thanks. This is good to know. And there is no problem. I will explain everything in Python. I think it will be also very nice for you to learn Python. This is really, you know, the 2 days you need to know Python because you have all the libraries available open source for free. And nowadays with this AI and everything, I think you can easily do all this modeling then with Python. Also actually for the characterizations for experiments, because when you create the data, you have the data sheets, and then you need to analyze, and then you can do the analysis in Python. I would strongly recommend to do all analysis in Python. Just upload your experimental results from characterization, for example, calorimetry, I don't know, TGA, thermogrammetry, to determine the, I don't know, Portland diet content. You can do everything in Python. I strongly recommend you. From now, just use Python. No Excel anymore. much more powerful. Let me ask you one more question. Maybe one from, just to know how much background you have in chemistry. Yeah, maybe this one. Do you see the question now again? If you can again answer. Now you see this kind of question. So the solubility of portlandite, if you would add acid, would it increase or decrease? Okay, a few more minutes. And the result, decrease 57% and increase 42%. Yeah, it will increase because we are making the portlandite more soluble, and this is also, you know, from the acid attack. And it's also acid-base reaction, so it will increase, and this is what we will learn next. Maybe let's do just one more last question, which is related to this one, just to explain better this one. Let me find it. Yeah, this one. Okay, so now you can already take part on the survey. This is the question. Solubility of portlandite if you add calcium hydroxide. So this is what you have also in Portland cement. You have always alkalis. This is why the pH is high. So will the solubility increase, decrease, or will it not change? Okay, we got the result. Let's see. So now you improved. Congratulations. So my explanation was good. Yes, the solubility of portlandite will decrease. And this is the well-known principle in chemistry. It's called common ion effect, because we have this, common ion, OH, and this is pushing increasing the concentration of OH in the solution, and that's why it is decreasing the solubility of portlandite. Okay, very nice to see how much 71% were correct. Yeah, thank you. So now I will explain the fundamentals. So now we dive into the solution of chemistry solution and the equilibrium constants. So for now we were just in the solids, but now we want to see, because all these processes are actually via solution. So that means the whole chemistry is driven by what is happening in the solutions. That means the ions dissolved in the water, they basically derive the chemistry. All the precipitation, nucleation, dissolution, everything is driven from the solution. This is why it's important to go into the chemistry, and this is what also GAMS app will do. The model we did before was just direct from solid to solid, but the thermodynamic modeling actually goes through the solution. So it calculates the equilibrium constants, and this is what I explained here. This one doesn't want to run. This is what I explained here with water auto dissociation. Basically, when the two water molecules hit each other, there is also always very small amount of H plus even in neutral water, and this is why we have the pH 7, and basically the pH 7, I will explain you how you can calculate here. Why the pH 7? What does it mean? The pH means the negative logarithm of H plus. In general, in chemistry, like in physics, we use logarithms because we have a huge range of, the values. It can go from 10 on minus 23 to 10 on minus 10 plus 23, like the number of in Avogadro. So it's a huge range, and then we need to use logarithms to be able to make sense of this huge range, to even visualize in one graph what's happening. And this is why we use logarithms. But basically, it's when you use the equilibrium constant, which basically tells you how much of this H plus you have in water, in the pH 7. So, and it tells you can calculate this by knowing by measuring, for example, the amount of H plus, which is basically the pH measurement. You see it's 7 for neutral water. And this basically, first you measure that you have only what is the concentration of H plus, and you can calculate it by reversing the logarithm. So the 10 of the power of minus 7, this is the amount of H plus you have in water. So 10 on the power of minus 7, because if pH is the negative logarithm of concentration of H plus, then the concentration of H plus is 10 on the power of minus 7. So small H plus concentration you have in water, and this is measured. And then you know that you also have so much of OH minus, because it's just pure water. So this is what you measured, and then you want to model this, and you can model this by the principle of equilibrium, so that you say that the concentration of H plus and of OH minus is constant. Why is this important? Because you can, when you change the H plus, you are also changing the OH minus. So you cannot define the equilibrium by just saying what is the concentration of H plus. Of course, the OH minus is connected, but this is because of this model. But the most important is that you should fix the multiplication of all the ions, and this is constant. So that means that you can increase the H plus, then the OH minus should decrease. So this is what we had before, if you know the solubility of portlandite, and this is we have put the common ion, which is the OH minus with calcium hydroxide, So we put it inside, and because this constant should stay the same, it can only stay the same if if you move the OH minus by precipitating more Portlandite in that case. So this is why the solubility of Portlandite decreases if you add OH minus, because this multiplication of concentration should stay constant, is always constant by certain temperature, and it can only stay constant if you precipitate. So you are producing more calcium hydroxide then until you get the same concentration which was the initial concentration. So this is why you are basically decreasing the solubility of Portlandite. But you are not decreasing until you reach the the initial OH value. You are also changing the pH. So just remember, in the solubility is defined by the solubility product, which is the multiplication of all the ions of that for example, solid. So for the solubility product for calcium hydroxide, I don't know, I have it later. The solubility product for calcium hydroxide is the concentration of calcium multiplied by the concentration of OH minus, but on the power of 2, because here we have the stoichiometric coefficient 2, so this should be the power of 2. So this is just mass balance. This is the law, it's called law of mass action. So if you apply mass balance to the chemical systems, you have the concentrations, you have the amount of ions in the solution, you have the solid, and if you want to apply the mass balance, you are basically end up with, you need to reinvent basically the concept of solubility products, which is telling you that the multiplication of it's called ion solubility product, which is the product of all concentration of ions, is equal to the solubility constant. And this is constant, for example, for Portlandite, this constant is 5 to the power of 10 of minus 6. And any equilibrium actually, it's also dividing by the, any equilibrium has the, what we have here. It's also always what you have on the right hand side divided by what you have on the left hand side. But the left hand side is, if it's solid, is 1. And if it's, if it's water, is also 1, because it's also the solution. It's everywhere. But if you have any other equilibrium constant, you should not forget to also put down in the numerator. No. Yeah, down you should put also the concentration of the left-hand side. But here, and also in the solubility product, because we have the solid, this is the concentration is equal to 1. So now we can see this example, and we can see that actually we know the solubility product, so we want to calculate the solubility. So then we just plug in the value for the solubility, and this value here, and we have two unknowns. We have the unknowns calcium and unknown of OH minus. And the trick for this is that you just say that you know how much calcium or OH minus is dissolved, this is the X. How much you dissolve is X. So the solubility is basically X. This is what you need to see here. And this is what we're calculating, the X. And then if the solubility is X, then we have here 2 times X, because we just have 2 times more just from the stoichiometry, because of this stoichiometric coefficient 2. And then we have only one unknown, and this is the X. And then you can calculate the solubility. So you plug in this X to the 2X on the power of 2. So we have 2 times 2. We have here 2 and the power of 2, don't forget. And then you can solve for X, and X gives you the concentration of calcium, which is also the solubility. So the solubility of Portlandite is 10 of the power of minus 2 moles per liter. This is how much calcium hydroxide would dissolve if you put, if you have a saturated solution. So if saturated solution means it is in equilibrium. So if you have enough portlandite to dissolve, you will have a saturated solution. So if you add more calcium or more OH, you will have precipitation. It's like adding salt in or sugar in your tea. So if you put too much sugar, it starts to precipitate. And just before it starts to precipitate, this is the saturated solution. So that means that everything is dissolved. Of course, also if you put too much, you still have saturated solution. And no matter how much sugar you put inside, your solution will always have the same amount of sugar. It will not dissolve more, because the more you put, it will always precipitate. It will not dissolve. So saturated is always the same. And this is this constant, solubility constant. It gives you how much of your sugar you have in your solution when you have too much sugar in your tea. That's the idea. But because here we have two ions, and if you have now potassium hydroxide, you are increasing the amount of hydroxide, and then you will have to precipitate more, and then you will decrease the solubility. So this is the concept of common ion effect. And I can explain it more here with more equations. So now we have our solubility, we have our portlandite here on bottom, we have our ions here. They are saturated, that means we have saturated solutions, we are in equilibrium, we can calculate exactly how much calcium and OH minus we have. And we also know how much portlandite we dissolved for this system to have so many ions. And this we calculated as a solubility. This was the previous example. But now I will explain, for example, there is one exercise that you should calculate the solubility of portlandite if you have, for example, you add base, which is the case of Portland cement. We have a very high pH, and this is because of alkalis. If you would have only portlandite in cement paste, no alkalis, the pH of pore solution would be 12.5, which is exactly what we calculated here, 12.3. This is the pH of pore solution if you only have portlandite. But because we have also potassium ions in the Portland cement, which are dissolving from cement clinker, this potassium is always hydrolyzing water, and you have the OH minus. So how many potassium? You always have so many OH minus if you have a pure system. But now we have a mixed system actually. We have a portlandite and KOH, and this OH minus actually is now adding here. So this will shift the equilibrium. It will precipitate more portlandite. And now you can calculate this simply by putting the amount of OH minus, because we know the pH is almost 14, so we know the amount of concentration. If you now plug in this value here, you can then calculate the new solubility, and you will see that it's decreased. If you increase this number, it will decrease the solubility, which is the X value, you know, the calcium. Basically the solubility is the calcium. So you are calculating how much calcium you are dissolving if you have already OH minus in your solution. And now you have, because you have a lot of OH minus, that means that you should have less calcium, because the ion solubility product should be constant. So you are increasing the OH minus, that means the calcium should decrease, because this should be constant. And this is now, you can calculate then the calcium amount, which is basically the solubility. So this we will exercise it later. Now, this is just to show you that actually it's a dynamic equilibrium, and if you know, if this is the law for the equilibrium, for the reaction rates, the rate for this is always proportional to the concentration. And if you have the forward rate and backward rate, actually you will have the equilibrium constant is just the ratio between the forward rate and the backward rates. So this is showing you that basically the equilibrium constant is derived from the dynamic equilibrium, because always the same amount of A that goes to B, then you also have the B going to A. It's a dynamic equilibrium. It's not, the atoms are not, fixed. They are moving, but the total amount of atoms in solution and the total amount is constant. But that atom is sometimes in the solid and sometimes in the solution. It's a dynamic equilibrium. Yeah, this is just to relate. So this is the ion activity product, what we said in a mathematical, if you would write it in a most general way. This is the P means the multiplication, and then you are multiplying all the concentrations, and then you are making it on the power of the stoichiometric coefficient. For example, you are multiplying for portlandite, we have the concentration of calcium, concentration of OH minus, and then on the power of 2. And this is the ion activity product. And if the ion activity product is equal to the equilibrium, we reach the saturation. We reach the equilibrium. I mean, that's the saturation. And any further ion you put inside, if you reach saturation, you will start to precipitate portlandite. And that ion can be either OH minus or calcium plus, 2 plus. So any further ion starts to precipitate portlandite. If you are your ion activity product is below the equilibrium constant, you don't have any precipitation, and then your solution is undersaturated. So that means that you are have your ions, but they didn't reach this ion activity product, and you didn't reach the solubility constant. You didn't overshoot it, and then you don't have any precipitation. So you can have undersaturation if you have 2 less ions. You have saturation if you have exactly the amount of ions that you reach equilibrium, and you can have oversaturation. That means that you have more ions than needed for saturation, and all these more ions will then precipitate solid, and then again you have exactly saturated solution plus the solid. I hope this, basically it boils down to this equation, and that you remember that the equilibrium constant, it's determining the saturation level. All this can also be, you can also do it with thermodynamic, with energies. This is just mass-based law of mass action, just doing mass balance, but you can also do it with energy balance, and then you end up with Gibbs energy, but you don't need to know this. Just GAMS is using this energy optimization. It's just another way of calculating the system, but basically there is a relation between the energy and the equilibrium constant or the concentration. And just when you sometimes see this Gibbs energy, that there is a relation between equilibrium constants and Gibbs energy. But this is much way easier to think in terms of equilibrium constants, because then you are just basically doing mass balances, which ends up in this example. One more thing, just for the kinetics. I told you kinetics in the solution, but because we are dealing here with solids, and we need to know there is another rate. There is another relation for kinetics, and this is that the rate of the dissolution or precipitation is basically proportional to the surface area. That's why the higher the surface area of clinker, the more reactive it is, the more hydration reaction is faster. It's proportional to the constant. This is the fundamental reaction constant. Surface area, you can measure it. And this is the thermodynamic driving force. So this is basically how far are you from the saturation. If you reach saturation, the ion activity product will be equal to K equilibrium. So basically this is 1, and you have 1 minus 1, you have 0. So in the saturation, your thermodynamic driving force is 0. And that's why the kinetics is 0. You reach equilibrium. And the more further away you are from the equilibrium, so if your ion activity product is 0, for example, when you mix cement and water, in initial millisecond, when you start to dissolve cement, basically you don't have anything in a solution, any ions, any calcium dissolved. So this is 0, the ion activity product is 0. So you have 1 minus 0, so your reaction rate is maximum. So yeah, so the rate is proportional to the ion activity product, surface area, and you have a constant. And this is true for dissolution and precipitation. And there are models, there are in geochemists models applying this kind of equation, and you can model Portlandite dissolution, you can model cement dissolution, and also precipitation of hydration products. So it's a dissolution precipitation reaction. And both are governed by the ions. So the more ions you have initially the hydration is fast because you have less ions, but then they start to accumulate. Then you have oversaturation, and then when you start to have nucleation, you start to precipitate, you know, the hydration products, and then again cement clinker can again dissolve because you again start. That's why we have also setting time, because basically in the setting time you have too much oversaturation because you need to form first nucleuses, and then later when the first Portlandite is formed, then you start to nucleate. The concentration in ion solution drops down, and then you have further dissolution of cement clinker, and then everything starts to go in this. It's called Le Chatelier process. Everything what dissolves again precipitates, and then yeah, you are basically near equilibrium, and everything what dissolves also precipitates, which is amazing system, which is not so common in you know, in that it's so perfect that it can work like that, that it doesn't, you know, enter diffusion or stops or doesn't react or reacts too fast, and then you cannot mold it. It's almost very unique system that you can have, you know, like hydration for years, and you can always dissolve and precipitate without blocking the, you know, the hydration. I'm always amazed how this is possible. Because when you do any kind of, when you start to mix something, precipitate something, it always stops, blocks, or happens something to block the reaction. But here in Portland cement, it really continues to react. So basically this is what I wanted to show you, and then later we will go. Don't be afraid of these equations, because we will anyway use also online tools. But basically you just need to remember that we have the ion activity product, which is the multiplication of ions. And if this is reaching your solubility product, then you have the equilibrium. So this is the rule for the equilibrium. And if it's, so we can also put a solubility index if you put a logarithm. Yeah, I don't know, chemists always like to put logarithm on everything. But then if this solubility index with logarithm, if this is bigger than 0, then it's oversaturation. So that means it may precipitate. Here I like the word may because, you know, it's exactly nucleation. You need first nucleuses and then it can precipitate. You have this like an energy barrier to form first nucleuses. That's why we have the setting time. And then when they form, then everything starts to precipitate, and then you are in equilibrium. But before forming first nucleus, it's oversaturated. So it is oversaturated and you don't have any precipitation, and this is because of the nucleation barrier. So this is why I like this word may. So you can be oversaturated and you still don't have precipitations because you need to nucleate. And then usually you need to overset a little bit more, then the driving force is higher, and then you can start to precipitate. Or if the saturation index is less than 0, then we have the under saturation. So that means that you are basically dissolving. And you can dissolve. This is for what you have with leaching. If you have, CSH products and you start to leach out, you are basically undersaturating the solution, and then you are dissolving the portlandite first and then CSH next. So you are leaching out the CSH phases, which is also with acid attack even more pronounced, because again you have this common ion effect. So this is basically, we will play with Aquion. This is like a Frixie tool, the very online tool that we can play with these models. And we'll go through some examples. This is how the tool looks, very easy. You just say what you want to react and how much, and then you can check how much does it precipitate or not. So this is what we will play with, just that you really get the concept of the saturation, undersaturation. And behind this is the Frixie calculation, which is doing all this speciation modeling, what I just showed you. And with this, I would like to conclude. Yeah, this is the SEM bridge in Cambridge. I was there in a calcium aluminate conference. It was the first conference after the COVID, I think 21, 22 more maybe. And on calcium aluminates was a very nice conference, but I like this bridge. It's called mathematical bridge. In SEM bridge, I think inside here somewhere is the, Newton's apple tree. And there is also Cavendish laboratory, where famous all this. So Cambridge is really a nice place to visit. And this is a wooden bridge, mathematical bridge. And I called it SEM bridge because we have in DFG, it's a national research funding from Germany. We have a project called SEM bridge, which is actually doing atomistic modeling of cement dissolution. And we call it SEM bridge because we are bridging